Hi, I'm Zeynep Kahraman from Group5. In this video, we are going to present our final project WhiteBox Fuzzer for the course EC504 Advanced Data Structures. The other members of our team are Caitlin Walsh, Hang Luo, Josh Manning, and Kübra Çilingir. The agenda is as follows. First, I'm going to give an overview of the problem we have and the solution we propose with some background of fuzzing. Then, Hank will talk about design decisions we made for our project while mentioning the underlying reasons and the possible drawbacks. Following him, Caitlin explains future innovations added to the design. Lastly, Joshua will show a small demonstration of our implemented WhiteBox fuzzer. The aim of this project is to design and implement an efficient fuzzer to detect vulnerabilities of a Java program. It will be fed with a single-file Java source code, representing a program that produces an output based on one command line ASCII argument. Hence, the goal of our fuzzer is to quickly find the string argument that causes the program to crash, such as a health with an exception. The catch is that there may be more than one such inputs. The solution that we proposed is to produce all possible strings, since the length is bounded, and consequently to feed the source code with them to see which input caused a crash. Our fuzzer is a WhiteBox fuzzer because given the problem statement, we have already learned some aspects of the source file. That's why we have implemented a generation-based fuzzer so that we can generate all possible test cases. So, why is fuzzing important? We often write codes to accept a certain range of expected input. But what happens when a non-expected input is injected into the program? If input isn't properly processed, then there are vulnerabilities in our program that can be exploited. Fuzzing helps us to identify them in an automated fashion. When we make an asymptotic analysis of our proposed solution, we observe that the runtime increases exponentially with respect to the input size, which is actually the length of the injected string. The reason is that to detect a crash, one needs to check every possibility. This is a similar issue encountered when we were discussing sublinear search in Lecture 6. Therefore, even though our fuzzer is very effective in terms of finding a crash, we cannot say the same thing for computation efficiency. Hence, we need to find a solution to reduce the runtime.
Here's our static call graph we made for our project. As you can see from the graph, we have three major components. The first class is called main class, and it is where our fuzzer locates. First, we use Java streams to iterate all possible numbers of permutation given the length k. For example, we know in ASCII there are at most 95 printable characters. When k equals to 1, we will have the stream iterates from 0 to 94, which gives us all 95 printable characters. And when k equals to 3, it will iterate 95 to the cube possible characters. In order to convert a number to a string, we first convert them to a base 95 numbers, so that assuming the first printable ASCII character is a, then the number 0 will just give us the string a, and the number 95 will give us the string of AA at length 2, and so on. After we converting the number, the program calls another method which uses Java reflection to invoke another Java class in the Java source program. It is basically dynamic loading the class in another Java program. Also, we support the GUI, and it is up to the user whether to enable it or not while using the fuzzer. We started our project with implementing a very simple generation-based fuzzer. It was using the Java Standard Process Library so that we can compile and execute Java program within another Java program. However, this approach was super slow and we had to improve the runtime to meet the minimum requirement. Then we looked into Java Reflection, and just like the name suggests, it is able to inspect the other code in the same system at a very fast rate. For the infinite loop detection, we have learned that from the lecture, it is an NP-complete problem, which means there's no polynomial time solution. After discussion, we have decided to use a timer to time out a certain chunk of code if it's running for too long. Given we have a very large number of input arguments, for example, for generating all printable characters, permutation at length 5, there are more than 7 billion of them. We cannot just store them in an array list and process. Therefore, through a different Java API, we are managed to implement the fuzzer without causing a memory issue.
Our group decided to add additional features to our project to expand upon our work. Our first additional feature is the GUI. With the GUI, users can choose their input options and run the fuzzer in a more intuitive visual way. The GUI also offers the additional feature of letting the user choose arguments to send to the fuzzer, rather than generating all possible inputs. Originally, this feature was meant to only test for one regular expression input, but we expanded it to parse a text file of user arguments. This feature is useful for users who have more knowledge of the code that they're testing beforehand, as they can quickly specify arguments that they suspect could crash their program without going through all inputs that they know are okay. The one major flaw of the GUI is that the user needs to restart for each fuzzing test. This is because of the way we call our fuzzer. A GUI improvement would be to wrap the fuzzer in its own class and instantiate a new fuzzer object each time run is called. Our second additional feature was expanding our fuzzer to run tests on strings of up to length 5. Ideally, we would like all of these tests to complete in under 30 minutes. Our group did expand the fuzzer to generate and test these longer input strings, but we didn't quite get there with the runtime. Even with multi-threading implemented, 5-character input generation and testing does take longer than 30 minutes, since our fuzzer needs to test every input to find all arguments that crash the source program. The final feature we implemented involved expanding our code to attempt to detect which inputs would cause our Java source code to enter an infinite loop. This is also known as the halting problem. Since the halting problem is NP-complete, we decided to implement a timeout condition within our tests to infer the presence of an infinite loop. While this might not be 100% accurate in practice, it does bring the user's attention to which inputs cause the source program to time out. From there, users can do a more in-depth analysis of their code to see why these inputs would cause a timeout in the first place. So this is just going to be a quick demo of our GUI. Since most of the functionality of this project has already been shown, I'm just going to do one of the unique features of the GUI, which is selecting a user test file. So here we're selecting our text file, we're opening it, we can see that it's displayed. I'm going to enable loop detection, and then we can run the fuzzer. And we can see that it lists the tested strings of the user input file here, and it didn't find any crashes for this test, so that's good.
So this is the demo of the CLI interface of our project. So for this, I already added Fuzzer as an alias to the bash RC as per the install instructions. So that is why it works outside of the box. To show you what we should expect, if you go to our sample simple buggy program, basically we simulate errors by throwing exceptions. In this case, for lowercase z and capital X of a single input. You can see all the other ones that should also throw input errors. So for throwing it with a single input, it works as expected, lowercase z and capital X. If we do it with 2, for now, just to remind you, and basically to explain what we did, we permutate through the 95 ASCII characters that we chose as human readable inputs, and we basically iterate through a base 95 system, in which case which gets converted into an ASCII string. If we go back to the terminal now, it should be finished, and you can see that capital X lowercase a in fact does return errors. If we try it with 3 inputs, this will take a little bit longer, but and we will explain that we use Java reflections, which is a basically just an API similar to process. However, we found that it ran faster and allowed for quicker runtime and quicker testing of all the permutations, allowing for it to run within the necessary time frame that was specified per the project. As you can see, it already finished and in fact detected all the errors that we threw exceptions for. If we try it with a loop detection under a single loop, that is a different program actually. And in that program, basically, lowercase 3 detects makes it sleep for 5 minutes, which is a simultation of an infinite loop. If we run it, however, we'll see that it does not actually run for 5 minutes. It only runs for 5 seconds for lowercase c. We basically set it so that it timed out upon 5 seconds of the invocation of that reflection. And and we specifically say this is a suspected infinite loop. We cannot say for sure that this input would cause an infinite loop, but we can say that it is suspicious, and that was determined as a way to tell whether infinite loops are in fact happening there. Because the halting problem is a NP-complete problem, we were not able to basically find a actual infinite loop.